Hello everyone and welcome into yet another live stream, and today we will be talking about theoretical, I'm kidding, we'll be talking about chemistry. That's because obviously, as you all have noticed last time, we are in a very certain location, very certain and specific location, that location being University of Birmingham. And despite what I've heard about the city of Birmingham, the university is actually really nice, and what's especially nice is their lab division. Now, I have myself personally broken into this lab and took all the safety precautions to record the stream, but believe it or not, it just so happened that I was breaking in. There was someone here working on the weekends, which I didn't expect. And so I've chatted with them, I've talked, we exchanged some words, and it just so happens that that guy happens to be a specialist when it comes to solid state NMR and mechanochemistry. And wouldn't you believe it, those are exactly the topics we'd like to cover today. So wouldn't you just introduce yourself?
Whoops. Hi, I'm Flame. You might know me from appearances on certain live streams or a video last year
Yes.
on photoelectron spectroscopy, which is very different to what we're doing today. I'm doing my PhD in mechanochemistry and solid state NMR, and today we're going to do a few experiments to show it all off.
Real experiments. Before we proceed, I know it's a bit of a breakage of fourth wall, but I just want to make sure everything is working properly. And it looks like speaking this guy so long, my goodness. Flame, come on. Sorry, Flame. There's this guy in my chat.
Yeah, don't worry.
So far, I would assume the audio is fine, the video seems fine, everything seems fine because no one is complaining. And to quote Katsi, and he is hot, as his name would suggest. So at least we got that squared away. First of all, should we start with running the experiment right away, or should we start with a bit of a talk about? Because the talk was
let's maybe talk about what we're doing.
Yes.
So my PhD initially, I was going to be doing working on materials called perovskites, which are optoelectronic materials, which means they do something with light and something with electricity. That makes them useful for solar panels because you can shine light on them and they'll produce a current. That's what I started with for my PhD, and then very randomly, I've been doing a side project on a completely unrelated thing, which is recycling Teflon. Which you might think, what's the connection? The connection is the mechanochemistry and the solid state NMR.
Yes.
So mechanochemistry is it's like a different way of activating chemical reactions. So traditionally you have photochemistry, which is activating reactions with light. You have normal solution chemistry where you just heat things up. So that's with heat. And you also have electrochemistry. What we're doing in this is you're quite literally just smashing samples together and the mechanical force makes them react.
Yeah.
And that lets you do some really weird chemistry. Like, for example, pulling apart the carbon-fluorine bond in Teflon, which usually is impossible to do because Teflon is known as the world's least reactive plastic. So we're solving that problem with mechanochemistry, and it's actually really easy, as we'll see today.
So I would like to first mention a bit of a disclaimer, because throughout the course of this live stream, I imagine I will be making fun of mechanochemistry quite often. And that is simply because I think it's comical how the other three types require some pretty good understanding, pretty decent technology, whilst mechanochemistry is basically hitting things with a rock. However, I don't want this to be misunderstood. When I'm making fun of mechanochemistry, I'm making fun of how simple the process is, despite the impressive yields. The actual reaction is really impressive when it comes to what you can get, because once again, that point should be stressed. Recycling Teflon, one of the reactive plastics.
The least reactive.
The least reactive, yeah. Even.
Yeah.
So reacting the least reactive plastic is a mighty feat, I would say. So should I, by the way, bring the camera closer for the...
Yeah, we should show what we're actually doing.
Then I'm going to bring the camera closer. In the meantime, I'm also going to check how is everyone doing.
I'm going to grab a couple of things.
All right. Okay. Closer. Actually, can I place it on this? I know it's
Um,
iffy, but
Yes, yeah, you can.
okay.
Yeah.
That would be actually really good and convenient. You all have to excuse the relatively crude setup, but I want you to realize is that we are in a genuine lab. I have been joking about in the past. I have been making some chemical experiments funny in my videos, but right now we are in an actual and genuine lab, which means safety precautions have to be taken and you know, the least reactive plastic. No, I mean the least reactive plastic that is really impressive of read. Okay.
So, I suppose we should get some Teflon,
Yes.
which is over here. It's, it's just a bag of Teflon. It's plastic. I should draw the structure as well. Do I have that? Yeah.
Safety precautions, we don't have those in theoretical physics, just saying. Yes.
I'm just drawing.
That's fine. In the
I
meantime,
realize I've just drawn
no, it's
too
fine.
many
In the
carbons.
meantime,
I
I
need to
can
draw points.
excite everyone with the angle of what is going to happen soon. And so, just to clear everything up, mechanochemistry is very descriptive in its name because it is exactly what you'd think it would be. It's reacting using mechanics, with using mechanical force. So, just like you can have with electrochemistry, is the one I have demonstrated previously by making sulfuric acid from copper sulfate, in which case the cost for your reaction is the fact that you're constantly pumping in electrons. In this scenario, by current, in this scenario, the cause of the reaction is mechanics, which will literally mean, grinding. That's once again cavemen hitting fire with a rock. I think shown in
Yeah.
front of the
So
camera would be fine.
there's a quick doodle I've drawn here. So on the top, is this? Do
What
you
do you
want to just
think?
hold it?
I can just hold it. Yeah, that's fair. There we go.
So the top is Teflon, which is a polymer, which means the structure kind of goes infinitely in quote marks. As you can see, it's just a chain of carbons that have fluorines stuck to them. And one important thing in chemistry is that the carbon-fluorine bond is very, very strong. And so Teflon is very unreactive because it's just covered in carbon-fluorine bonds. So you can't really react the carbons with anything because they're bonded to fluorine. And the fluorine is just kind of hugging the carbon. So typically, Teflon just won't do anything. And this is why it's used
So it
as
has like a
a
very thick protective shell of
yeah,
fluorine.
yeah,
You need
pretty
to
much,
nibble at
yeah.
its inside instead. So, so it's basically an exercise of how do you break apart through this very tough to break through shell.
Yeah, yeah, and so Teflon's used as like the non-stick coating in pans, if anyone knows that, which I think most people do, because it's not meant to react with anything, so it won't stick to anything, and your food will be safe, even though it's touching fluorine atoms. But today we're gonna break Teflon apart.
Yeah, that makes very much sense. Once again, breaking apart the least reactive plastic. Yes, and no one seems to have any questions or confusion, but everyone still seems to be quite excited, so that's good. Because what you're about to see is real cutting-edge chemistry, which I would say is quite exciting.
Do I have calcium somewhere? I do.
I also like the contrast between the two methods of mechanochemistry and NMR, a solid-state NMR, as the two topics to cover, where how incredibly specific and like high tech one of them is, and the other is
Yeah,
mechanical.
there is a lot of theory in mechanochemistry. Most of the theory is not very well understood right now.
Oh,
So,
that's another thing that we could mention as a very interesting thing, which is that mechanochemistry, despite its simplicity, is a pretty new and emerging field.
yeah, yeah. So even though mechanochemistry dates back to the invention of fire, because striking rocks together and making a spark is mechanochemistry. Um, Even though it dates back very far, it hasn't really been used in chemistry in a while. Uh, and so only recently, basically the last 10 years, it's become a bit more mainstream. I personally think it's going to become very, very mainstream because it's really powerful. It lets you react things really quickly and without solvents, which most people imagine chemistry has is mixing liquids together. We get to do this without liquids. We
Yeah.
get to just throw things in a container.
There is also a question, why calcium specifically? Why, I don't know, not some other metal?
There are other metals that work. For example, magnesium, which is in the same group as calcium, that also works. But that reaction with Teflon is a bit explosive sometimes, so we're not doing that today. Uh,
Yeah. Smashing things against each other is the true scientific process. You heard it here first, folks. It's only for physics, it also works in chemistry.
so, I have two containers. And I've got calcium metal. I don't know if this shows on the camera very well, but this is just pure calcium.
Bit dark, but I think it kind of shows.
I mean, I'll take it out in a minute.
Yes.
Do we want to just do the reaction now?
I reckon we could. So once again, I know I keep repeating myself, but I want to. It's really easy to get lost and not actually realize that's what's actually happening. This is just Teflon.
This is just plastic. It's Teflon.
Yeah, it is just straight up the least reactive plastic,
Yep.
and we're about to react it in front of your very eyes.
So
It won't be instant though. Temper your
I'll get a
expectations.
few pieces.
Takes half an hour. And as expected, everyone instantly switched to talking about eating calcium in unison.
Of course, yeah.
Yep. That's
So
it.
one of the advantages of this reaction is that calcium is not very toxic. So you could literally do this with bare hands.
That is actually pretty impressive because recycling the least reactive plastic is one thing, but doing it safely is another.
So yeah, I'll get a few pieces here just to show the camera. This is calcium. It's just a metal. It's in your bones as well. Hopefully.
Not anymore.
Make sure it's in your bones. And I'm just gonna put a few pieces in. So normally we would calculate the correct ratio and weigh out the correct amounts. Today we're just gonna ball and
Because we're gonna ball on so many levels.
yeah, maybe this needs a bit more Teflon. So after we do this reaction, we're going to quantify how much is actually reacted by doing solid state NMR. I think I'm going to take a piece of calcium out just because I put too much in.
I hope no one is confused yet. Because once again, I don't listen. I'm sorry, I don't mean to constantly make fun of mechanochemistry, but it's an instinct.
So the way this mechanism works is it's a container that has two halves, and we also put a steel ball inside. And this steel ball, so here's this machine that will shake up the container, and the steel ball inside will move around rapidly and crush up everything in the reaction vessel. And so it's basically applying very high localized force. So let's stick this in here and close it. Push the Teflon all the way. So I'm going to seal this so it doesn't come apart.
Now, if I'm not mistaken, there is an actual difference between mixing as a concept and mechanochemistry. As in,
Yeah, so
mixing isn't considered low energy mechanochemistry only. It achieves a different purpose.
there are some mixing techniques that are considered mechanochemistry, but what we're doing today is called high energy milling because the ball will generate localized hotspots of really high energy when it collides with stuff. I'm just checking this is closed properly. I think it's slightly, it's fine. It's not fine. There's a piece of Teflon sticking. Okay. So I'm just going to tape this shut.
Okay.
Okay, so it's taped shut, but there's still stuff inside. Don't worry, it hasn't disappeared. If you want to get the angle, show the angles right. This kind of clips on. And we also need another one here to balance the machine, otherwise it will rip itself apart when we start the reaction. So let me get another thing to balance.
There we go. So what we have so far is, just show you. There we go. That's the basic idea. You put in between, you clamp it basically together in place, and then the machine is going to move it rapidly, which will result in the steel ball inside moving around, resulting in mechanochemistry. Wonderful. The Dutch angle. There we go. Tenet complete. What's the max speed shaking can go up to?
So this one will go up to 30 hertz, so 30, I guess, shakes per second. I don't know if that's like, if one way counts as a shake or if it has to get back to its starting point to count as one. I just know it says 30 hertz.
It does something 30 times a second.
I'm going to just set a very long amount of time and we will just stop it whenever we feel like it. Are we ready? Is
Yes.
chat ready for this?
Is everyone ready? Also, just in case, lower your volume, I think. I reckon that's a good enough warning. Alright.
Okay. It's not going to be very exciting. It just starts shaking.
Oh, it's gonna be tremendous. Are you ready? 3,
Yeah.
2, 1.
Boom.
Crazy stuff.
Mechanical
Explosion.
chemistry.
Yeah, and now we have to get back to it in 30 minutes. Actually,
Yeah.
how long? 30?
Well, we can leave it however long we want. So we eyeball the amount, and we're gonna eyeball
the time.
Yeah. We can come back to it whenever we feel like.
I like it because at the end we're going to have the data for just, we're gonna know exactly what the NMR spectra is for the eyeballed amount with eyeball time.
Yeah.
So that's nice.
Yeah.
So I reckon we will now go take a 5-minute break just to move the equipment to the other room.
Yeah? Yeah, let's go to the
So
other room.
we'll be back in 5 minutes. Don't go anywhere. And everyone, we are in fact back in a new location. I said we are, there we go, we are back in a new location with a notebook. That's because what we've just tackled is mechanochemistry. I hope everyone was paying attention. It will be important, there will be a test on it later. But after our reaction is done, we'd like to actually know what happened, right? Reaction on, so we need to somehow figure out if our Teflon reacted, how much it reacted, etc., etc., etc. So, how we go about that? Actually, because I think this one.
So I've just drawn the reaction again, but I haven't drawn the long chain. We've just put brackets on the thing to indicate that it's a polymer, and there's a small n here to show that this kind of repeats any number of times. This reaction is quite straightforward, and what drives it is that the calcium fluoride is really stable. It's just hard to do normally because you can't break this bond very easily. So with mechanochemistry, we get to overcome this barrier and go to the more stable calcium fluoride.
So basically, a simple principle of every chemical reaction ever,
Yeah.
except
Yeah.
right here we're dealing in some crazy extremes because both bonds are ridiculously stable.
Yeah, I mean, calcium fluoride, I'm not sure how stable it is. It's just pretty stable.
Oh,
It's just more stable. Like if you have your fluorines not attached to the carbon,
Mhm.
and you just have like the carbons and the calciums, they
You
would
would
rather
pick
be with the
calcium.
calcium. Yeah.
which
But it's just very hard to get
which
out
then
of this.
makes sense because then effectively, in order to recycle the Teflon with mechanochemistry, our entire goal is to break the carbon-fluorine bond.
Yeah, yeah. And so the keen-eyed chemists among you might look at this and be like, why the hell is there just carbon? It can't usually do that. That's a good observation. It's basically just that carbon in this form is bonded to itself. So in reality, this is like some whole network of carbons. You know, they're doing whatever they want. And they might also pick up some hydrogens from the air. They also might pick up some oxygens from the air or some OHs. So these are all components of water, H2O. But in the end, you'll end up with some structure that's a lot like graphite or graphene. And so we call it amorphous carbon. It's essentially coal that you end up with. So we've taken Teflon and calcium and we've made calcium fluoride, which is a very stable salt. It's kind of just a mineral that you can find. It's called fluorite, which is there's a tangent there about fluorescence coming from fluorite, which this by itself isn't fluorescent. The fluorescence comes when this has other stuff in it. But yeah, this is fluorite, and this is basically just coal that we're making.
So once again, on the left, you can see your infinite Teflon chain, which is reactive, and to it calcium, which we have shown. So on the left, that was the white bits and bobs and pieces from the bag. Then next to it was calcium, the rocks you all wanted to eat. I feel like I'm talking to a child. And then on the right, we have calcium fluoride and then random carbon chain.
Yeah,
as you mentioned.
yeah,
Oh.
it's like a network of carbons. Obviously, we're not forming diamond, but diamond is a network of carbons as well, all bonded to each other. It would be really cool if we were forming diamond, but we're not because that would break the ball mill. So yeah, so the question is, how are we overcoming such a high energy barrier? And so we can go into a bit of theory here. All the way back a year ago in our photoelectron spectroscopy video, we were talking about barriers and energy levels for molecules. And so we can draw a graph that's like this, and this is R. So this is our bond length. So if we have two atoms, let's just draw an atom here and an atom here. These two atoms are bonded together, and if you try and pull them apart, they will spring back to this position. And if you try and push them together, they'll spring back to this position. So there's some ideal position that they want to be in. And so the curve that we get for that, if this is our energy, is something like this, where this point is the most stable bond distance for them to be at. So you can imagine if you try and push them together, you'll be going up this curve, and then if you and so you're increasing in energy, and they will want to come back down here. So it means our bond basically acts like a spring. So it's more like they're attached on a spring, and then you could model this as a
Harmonic oscillator.
harmonic oscillator. Funnily enough. And
do you
so, yeah, we talked before about the quantum harmonic oscillator, where these energy levels are quantized. We're not going to bother with that today because it's not really relevant to what we're doing.
Funny enough, soon enough we will get to this exact graph from a quantum mechanical point of view because it's not that far of a stretch. But yeah, the basic idea being there is a very visual way to think about it, which is that if you have just two atoms, if you squish them too close together, then obviously they want to repel.
Yeah.
Push them too far, their electrons no longer going to stick them, and this is what we get.
But in the context of mechanochemistry, when we apply a force to our molecule, what we're essentially doing is on this curve, we're applying a new potential line, which is, it can be drawn something like this. So it's a straight line with a decreasing potential. And so what this line is saying is basically, this is a model for if you're pulling apart our atoms. What this line is basically saying is when I'm trying to pull apart the atoms, they want to move apart. So if we forget about this curve for a second, if you were to just have a bond length on here, they would just fall off that way. They would infinitely increase in length. Obviously, when we account for this, what we basically have to do is just add this to this.
Yes.
And so what that looks like is something like this. I don't know if this is very visible.
Yep, it is. I just need to zoom out, and yep, it is.
So it looks something like this, where now there is still a bit of energy required to go past the stable bond length. But if we go past it, now they will just fly apart from each other. So this is like a good model for understanding how forces can actually affect bonding. Obviously, this is only a model for two atoms bonded together in the most simple way possible. But when you have full molecules, the same kind of behavior can happen. So normally with molecules, instead of this being just a line, you will instead have this in 3 dimensions or 4 dimensions or whatever. And when you apply some forces, depending on the directions the forces are acting in, it will modify that potential in some way.
It's always going down, always making it more likely for them to drift apart, or rather allowing them to drift apart.
It can be. It can also not be. So it's not always. Because, for example, if this potential was, if instead of applying a pulling force, we were applying a pushing force, then the potential would be like that. Yeah. And so it then depends, does this, where's the negative part of this line? If it's negative here, then this will still go down. But it just depends on how you actually define this line.
Yeah. Does anyone have any questions so far? By pulling apart, you mean yeeting a rock at one of them? Yep, mechanochemistry.
Yeah.
The same way you break an object if you threw something at it.
Same way you'd break an object if you threw something at it. I think that's, yes. I think that's correct.
Yeah, like on the surface of an object.
Yeah, there are extra things at play with that because it's like when you have like an ionic solid, it's brittle because as soon as you move the atoms a bit, they will become very unstable because you have positive stuff next to positive stuff and negative stuff next to negative stuff. When you have something like Teflon, it's a lot more flexible. So it's a lot harder to break it apart. So if you were to just put the Teflon by itself in the mechanochemistry in the ball mill, it usually just comes out as like flakes. It doesn't actually break into a powder. So we require the calcium to be here to make the reaction happen. So it's more than just breaking things apart. It's actually, it's providing another pathway for these atoms to go down.
So yeah, so basically, the purpose of mechanochemistry here, am I understanding correctly? The purpose of mechanochemistry is just to allow the fluorine to just get removed from the Teflon. It's the first step, that is, make this potential which allows the
Yeah,
fluorine to
yeah.
detach
It's
from the substrate.
we're still not sure what the exact mechanism of this is, so we're trying to figure it out.
That does make sense.
But we we speculate that yeah, we could be forming fluorine radicals, which is just if the fluorine was just getting ripped off by itself temporarily, and then those radicals can go on to react with calcium, or they could even react with the container, which we do see some like corrosion of the container in some of our reactions. So that's a potential avenue. We've been trying to check that with like
Actually, I
EPR to
haven't
see
asked,
if there's
are all of the
radicals.
containers steel?
Not all of them are steel. So we mostly do them in steel, but we also have zirconia containers, and we have tungsten carbide containers. When we do the reactions in tungsten carbide, they don't corrode the jar. So um,
Let's just also ask, what are your majors?
what are my majors?
Yeah.
Uh, I did a I did a master's in chemistry, and I'm doing a PhD in chemistry. I don't.
Really?
Yeah, crazy.
Oh, I'm
Yeah.
shocked. I thought you were studying history. Well, in that sense, because now there's a very reasonable follow-up to this, I would say,
Yeah.
which is that we have, well, like theoretically, we have broken up our Teflon, and we have broken it up. We should get coal, we should get this, but the question is, how do we actually figure out if we have gotten it? How do we measure?
Well, it's funny you should mention that because we have a very useful and very powerful technique called solid state NMR. And if I can just pan this up a bit,
Find this up, yeah. And would you like me to turn?
this is the NMR computer.
Would you like me to turn left, maybe?
Yes, yeah. Look at the magnet.
And so if we turn left, we can see this massive giant cylinder column it's actually not doing, I feel like because of the angle, it's not doing it justice. It is, yeah.
So
A magnet.
Yeah, I'm gonna take my microphone off because
Okay. In the meantime,
'cause it's a
I'm going
magnet.
that is true. Safety precautions first.
so
You will mind me briefly. I also need to.
this whole
Hold on.
thing has
Oh, hold on for a second. Just.
magnetic field.
Yup. And it is working now. Yes.
Okay. So yeah, there's a massive magnetic field on this thing. If it picks up my big magnetic field. I mean, there's so much I can explain. Let's actually start with this.
I think a good place to. Well, actually, that's a good question. What is a good place to start? It's a massive magnet. I really can't stress enough. I really can't stress enough just how enormous it is. Flame is right now standing on the ladder. I think a good place to start, I suppose, would be the purpose of the big magnet. And of the big magnet, yes. And then we slowly hone in closer and closer.
Yeah. So, how do I even start that? We might need to do some more drawings.
Everyone got hooked with a massive magnet, now they'll be ready to pay attention. I just party of Polish. Yeah. So, I suppose a first good question would be, what would be the utility of having such a large magnet? I mean,
Well,
if I know my magnetism, when something is magnetic, you need only small magnet to move it. So why would you need a big? Are you moving it a lot, or is it something different?
So the magnet creates conditions for an experiment. And I'll put my microphone back on.
Yes.
So the magnet creates conditions for an experiment. And those conditions are the separation of the spin up and the spin down states of our, yeah, I should say what it is. It's our nuclei. So this is a technique called nuclear magnetic resonance. And so when you have a sample of something, it's Your sample is made of
I think
atoms
we should maybe
in
draw it,
molecules.
because
Yeah, we should
drawing
draw it.
drawing it will explain much. But the point is, we are starting with a big magnet. I will foreshadow a bit that there is more than one magnet at play here, and first we're going to explain the purpose of the big one, because I mean, obviously, most exciting.
Yeah.
The largest magnet in the UK, some people out there would say that technically there are largest magnets because poles and stuff, but largest magnet in the UK is specifically made for the same purpose.
Yeah, so I was I
this
was
is
there a couple days ago at Warwick University. They have the strongest continuous magnetic field in the UK, and
Which-
that's specifically for NMR, which is
Yeah.
what we're doing.
So what we're going to be explaining here is the purpose of the same magnet as the largest magnet in the UK. Once again, technically not the largest magnet in the UK, but I don't think singular pulses should be counted, and I'll let the pedantic
Yeah.
pedantic people who use those magnets go after me in the comments. That's fine.
So you have in any thing that exists, you have atoms, right? And I'm going to draw a really crappy high school drawing of an atom, which has stuff around it. This is the worst atom drawing I've ever seen, but we have our electrons, and we have our nucleus, which is made of protons and neutrons. So, I don't know if P and N are the correct terms, the correct symbols for those, but electrons, any individual electron by itself has a spin, so it can be spin up or spin down.
As
And
we have learned yesterday in excruciating detail.
yeah, and protons have spin, and neutrons also have spin. So spin is it's an intrinsic property of many particles. If you want to know where it comes from, that's a physics domain. Chemists just care that they have this property. So, what do we do with spin? Well, spin acts like it's as if the
As if it was
sample is
spinning.
yeah, it's as if the thing is spinning. So many years ago, the discovery of spin was when some guys, I think it's called the Stern-Gerlach experiment, so I guess it's Stern and Gerlach, I don't know. They fired electrons, a beam of electrons, through a magnetic field. That's a very sideways S because I'm sideways. But they fired electrons through a magnetic field onto a screen, and what they found is that they tend to accumulate in two very localized spots, which doesn't really make sense unless you account for the fact that they can be spin up or spin down. So it means that the electrons that are spin up will go this way, and the ones that are spin down will go this way. And what the spin represents is it's as if the electron is spinning on its axis. So if the electron is spinning,
I think the clearest analogy of this would be what happens if you have a particle and what happens if you have a charged particle, and
Yeah.
what happens if you wanted that charged particle that interacts with the electric field to interact with the magnetic field.
yeah,
And if some of you recall the Maxwell's equations, I'm pretty certain Maxwell's equations actually, I could be wrong on this actually, so whoops, doesn't matter. The point is, that when you have a charged particle, if you want it to interact with the magnetic field in this specific way, you want it to be spinning. You want that object to be spinning.
yeah.
Since if our particles interact with the magnetic field, therefore they must have this spin.
So we know from physics that a moving charge will produce a magnetic field. So if you have a wire with a current running through it, then it will produce a magnetic field looping around it like this. Alternatively, if you have a charged particle that's spinning, this will produce a magnetic field around it that way. So you can either have the current in one direction, which will give you a rotating magnetic field, or you can have the field, you can have the current rotating, which will give you a field in one direction.
And it is because Maxwell's equations have two curls. One causes electricity, electricity causes magnetism, magnetism causes electricity. Once again, the curl operator, curl nabla, which means they must go in a loop.
Yeah. And so this experiment showed that electrons work, but what we also find is that the nucleus of an atom is charged. It's just positively charged. And so in NMR, what we're doing is we're picking out the energy levels for these. And so normally we will have our two energy levels for spin up and spin down. And these two will be at the same energy. Because when you have just your electrons existing in the world, there's no reason for one of them to be pointing up or pointing down. But then suddenly, when you put your magnetic field around the whole thing, now these two energy levels will split. So one will go up and one will go down. And so this is basically if your nucleus is a bar magnet, so if your nucleus is a magnet, and let's draw it like this. I've drawn that really badly. Let's draw a bigger one. S and N. If you put this in a field that's like, then they will be more unstable in this configuration. And they will be more stable in this configuration. Because they want to be aligned with the field that they're in. And so the nuclei acts like mini magnets here, where they'll align with the field that you're applying to it. And what NMR is it's about measuring this distance between the two. So how do we do that? This distance turns out to be, if you were to do this transition with an electromagnetic wave, so light, this is in the same frequency range as a radio wave. So you're actually applying radio frequency pulses into your sample, and you're probing this transition. Is this making sense so far? I feel like I should have planned out exactly what I'm talking about.
No, genuinely, this is I would say it's a really, really good and intuitive explanation. And so far, Remco said yes, but how do you find the distance between the two is a follow-up question, which I would say it's decent. It's a decent follow-up question from.
What was the follow-up question, sorry?
How do you find the distances between the two levels?
How do you find the distances between the two levels? Yeah, so
because that's the rest of the machine.
that is what NMR is. It is about finding the distance
because
between
what's
these.
funny is that what should be, I feel like that I really don't want that point to be lost, because I find that point to be comical, which is that the big magnet, it basically causes them to split.
Yeah.
That's basically what it allows you to do.
Yeah.
That's it.
That's it. So the whole big magnet that costs however many millions of pounds, I think this one costs 1 million, and then it costs £1,000 a day to be maintained. The whole point of that is just to split these energy levels. That's all the magnet does. And then we've got all this other equipment to do an actual experiment on the nuclei.
Shall we show the next part and explain the next part, or do you reckon some more theory?
Let's talk very quickly about what we're actually doing.
Yes. Okay.
Which is actually, yeah. Should we show? Let's show. So I'll just talk quickly about the radio frequency pulses. So the machine will apply a radio wave to our sample. The thing is, if you apply a very specific frequency of radio wave, and this frequency matches the gap, then you're chilling, and it will do the transition, and you will measure something. But if you apply it and it's the wrong frequency, then nothing happens. So how do you work out the correct frequency? What we do is, it's kind of a bit of cheeky maths at play. We basically just apply a very powerful and very short pulse. So if we apply a radio pulse that's very short, there's actually uncertainty in the frequency. And this becomes a question of Fourier transforms,
Yes.
which I assume most people are not super familiar with.
Well, I
but-
mean, my most popular video on the channel, they better be.
Is it? Okay.
But yeah, the basic idea. So because this should be, yeah, I to clear it up.
Yeah.
I don't know if I depend because everything you've written out tonight so far is very aesthetic. I feel like I'm gonna accept all
Feel
these.
free
Yeah.
to just.
So, very, very crucially, as we learn from quantum mechanics, and that's a quantum mechanics fact that actually is relevant, H and F, or H bar, F, doesn't matter. The point is frequency, or rather energy, is proportional to the frequency when we're talking about radio frequencies. That's why we care about frequencies, because that basically gives you the energy. So, when you have those two possible states, when your magnet separates them into two, the difference between them is effectively a question of energy, how much energy they have at each state.
Yeah.
So once we apply the pulse, that is basically us giving them that energy, very common theme throughout a lot of chemistry. The problem, however, is in the fact that we only have two possible states, correct?
Yeah.
Yeah, we only have two possible states, as we have learned yesterday on yesterday's stream. Only two are possible, and because quantum mechanics has this nasty property of being quantum, what this effectively means is that if you start at your ground state, if you give it a little bit of energy, so if we really briefly just draw it out as a ground state like this, if you have another state right here, then if you give it not enough energy, you're going to end up right here. But there's no empty state. You can't reach that point. If you give it too much energy, you're going to end up right here. But once again, how can you end up up there? There's no spot there for you to be. You need to actually hit it perfectly right at this spot, and that's the only place where well, I almost said electron, not quite, where your particle, be more general, actually hits that other state, and for that you need the pulse of perfect frequency, because once again, energy is proportional frequency, and that's all we actually have control over. And so then the Fourier transform trick, I'm thinking about how to explain the Fourier transform trick because it's very elegant, and it would be
I mean,
basic.
so the way a Fourier transform works is if you have a wave and you Fourier transform it, so you Fourier transform this, it will come out as some graph that has a peak at a certain frequency. So this is time, and this is frequency. Can't draw an F. The frequency value that we get here will match the frequency of this wave. And the thing is with this wave is if you let the wave go on for much longer, then this line will get thinner because you become more certain about the frequency of the wave the longer the wave goes on for. So if you have an infinitely long wave that goes on for an infinite amount of time, then your frequency graph will just look like this with a single line.
Yeah, so the reason basically why, I'm so sorry the camera wasn't, there we go.
Okay.
I'm so sorry, I should have fixed that as well.
Yeah, so your wave will go into a curve, it will get Fourier transformed into a peak on the frequency graph, and if the wave is infinitely long, then the peak will get thinner. Well, sorry, if the wave is longer, the peak will get thinner, and if the wave is infinitely long, then the peak will be infinitely thin.
Yeah, and the reason exactly why Fourier transform allows you to do this sort of thing is because if you imagine some kind of arbitrary wave like so, then if you imagine on top of it layered, so this is our imperfect wave, and then if you imagine a perfect wave, so its wave number k is actually constant and doesn't change across the wave, then it would maybe not align perfectly, maybe the wavelength would be slightly higher, and for that what the Fourier transform allows you to do is it basically gives you the value of k. Then if you have another one that is slightly smaller, it would align also worse off, but what you can see is that there is a gradient. There is, right here we do have a spectrum of how well it aligns. So if we have our wave with k equal to 2, for example, then k of 1.99 will align a lot better than a k of minus, well, just, I don't know why I went minus 0.5. K of 1.99 will align much better than k of 0.5, and that's what Fourier transform allows you to do. However, the shorter the wave, the less time you have checked the overlap between the two waves, which means that uh, basically the shorter the pulse, the more uncertain the wavelength is, and apparently this, I'm honestly baffled that this works out.
Yeah, so it's basically we just apply a pulse that's really short, and this means that when we Fourier transform it, we get into a curve that's like this, and so it's covering a very broad range of frequencies. We still need to be fairly accurate with this. We can't just do this and excite every nucleus in the sample. But what we can do is we can excite a specific type of nucleus. So for example, there will be one frequency range of pulse that you'll do that will excite all the protons in your sample, so all the hydrogen atoms. And there'll be another one that excites all the carbon atoms.
I do have a question actually,
Yeah.
because that is just a photon you're emitting. Is there any trouble with, instead of the nuclei being excited, the electrons catching them?
No, because the range for the electrons is completely different. The electron range is microwaves, and the nucleus range is radio waves.
That makes sense then.
Yeah.
That does make sense. Okay, is anyone confused about this so far? Once again, sorry, I bumped the camera. There we are. Zoom out. This is the notes. It appears that no, everyone seems to be understanding decently well. I'm guessing. Give me a yes or no. Everyone watching right now, I want to see if you're paying attention. This will be a test. I have all of your names noted down, and if someone doesn't answer and left during the stream, I will find you. I will find out where you live. Yes. All right. Thank you, Jasmine. I imagine, Jasmine, you would like that because I've seen you active often in the chemistry channel, so I imagine you would like this kind of stream as well. And it appears that, yeah, Ash is still thinking about how sharp cutoff results in broader frequencies, but I would imagine, Ash, it's simply because you're thinking about it really abstractly. There has to be some kind of
Well, so the drawback is the sharper you cut this off, the lower the actual signal is. So you make it broader, but it gets lower and lower. So you can make it infinitely broad, but then it will be infinitely small. So
important thing, because Timon just asked, what does it mean for a nucleus to be on a higher energy level? For an electron, it's a different orbital. What is it for a nucleus? Crucially, no. For an electron, it doesn't mean a higher orbital. Only, as we have learned yesterday, we have our quantum numbers. And I suppose we haven't gotten into it because interactions are unfortunately another kind of worms. However, your spin very much changes how your electron interacts with different interactions, specifically electromagnetism. And the very important thing here to remember is that depending on the circumstances the electron is in, its spin could lead to wildly different energy levels. In fact, I'm pretty certain there is some kind of experiment which, like, I vaguely remember it being similar, right? There's something.
yeah, so there's a technique called EPR, which is electron paramagnetic resonance, which is like NMR but on electrons. And,
Yes.
And that
so
uses this principle.
And so important thing, it is a bit abstract, so I don't think I have a great way to explain it, but the basic idea is you have your particle, and then you have your particle in different circumstances. And depending on the circumstances, the quantum numbers sometimes require higher energy than other times. And so in this scenario, the bar magnet analogy is brilliant because that's literally what it is. What does it mean for your bar magnet to be aligned one way or the other? Well, it's just direction of the magnetic field, and they would much rather be aligned with the field than against it. And as such, aligned with the field is lower energy than against the field because that takes you energy to keep it in place. Same exact principle for a nucleon.
Yeah.
And so makes sense that you aim for the cameras and don't forget something. So short pulse equals nucleus doing funny business. Not quite. Short pulse means there is a silly way to put it, I guess, which is that short pulse is basically tricking quantum mechanics into not knowing what pulse you're actually sending.
Yeah. So a pulse that's at the right frequency will make the nucleus do funny business, but in order to get the right frequency, we make the pulse short so that it covers a bigger range of frequencies.
I do have to say the Fourier transform is just a perfect example here, because Fourier transform, you have a function like this, just once again, just what flame draw, like this. And this function is very crucially, right here, you have your values of the wave number. So basically the frequency. What is the frequency of your wave? And the shorter the pulse, the larger it gets, because the more uncertain we are. Now what we're trying to achieve is reach this singular line right here. Only if our frequency is equal to this line will it actually excite, because there's only one other energy level. It can only jump by one. So right here, if only we achieve this perfect hit, we are golden. And so as you can clearly see, the larger, the broader the function, the more uncertain, the higher the likelihood is that we actually hit that bar.
Yep. Should we have a look at the magnet?
Oh yes.
Yeah.
I was hoping you'd say that.
Yeah.
Hold on. I will turn off the camera for just a brief second. No one panic. We're not going off the air, we're just relocating. Well, not really relocating on the...
We can give it a sec.
Oh, we could give it a second.
Or we can go to the back to the lab and look at the sample.
Mechanochemistry lab, you say?
Yeah.
That we could also do. So we're just flipping the nucleus spin with photons, because different energy levels. If I understand correctly, yes. You have one energy level that's aligned with the magnet, the other one that's counter to the magnet, and you need additional energy in order to reach the counter to the magnet. I actually think, yeah, we should go to the mechanochemistry lab. Everyone will be back soon. And there we are. We are in fact back. So, hope you all enjoyed your break. Hope you got your popcorn ready because there is a black screen and there is no longer a black screen, I said with confidence. There we are. We are back in the mechanochemistry room. And I would say you all better remember the mechanochemistry room because it was so long ago. If you recall, right here we have our Teflon with calcium. And Teflon very much doesn't want to react. But as you can see, we are using everything in our power to make it react because we are just so much larger and we just get to shake it violently. So, I'm going to position the camera somewhere nicely.
Yeah, I'm just gonna put some
With a nice
down.
Nile red angle. I do feel like a number file, especially when you were drawing in
Yeah.
the notebook.
Okay, so we can stop this. Nice and quiet now. And let's take this out. So this has been going for about 55 minutes-ish. And hopefully it's reacted. So let's see. Hopefully at least partially reacted. So this tape, I'll just leave on the side. We may have done a bit too much Teflon. This doesn't look good. This looks mostly unreacted. Maybe we go again. We can still do NMR on what's in here.
What does it look like exactly? Oh, there is white.
Yeah,
in the-
so it should be black. Me when the chemistry goes wrong. Maybe we shouldn't be eyeballing the masses.
Could we take a little bit of it out and add calcium to the rest? Or is the powder going to be contaminated?
I think the problem is that I used big pieces for dramatic effect, and they haven't crushed up enough in
Oh,
time. So usually we'll do it with some slightly smaller plastic pieces and some smaller calcium pieces. But this size has worked before. I think maybe the ball got stuck. I think we put too much in, and the pieces are too big. But we can still look at this. We can still inspect this. So I think we should put another one on, and we'll still measure this one in NMR, and then we'll come back to the new one afterwards. So we'll do smaller masses. So the only problem is I need a new container. I can reuse this container. It's fine. So let's take this out. Put it in here. And I need a spatula. Give me a second.
Yep. In the meantime, I'm going to... Actually, I shouldn't, I reckon. I was going to show you what it looks like, but then I figured that it's not really my lab, is it? Is the cylinder stuck? The balls are stuck in the cylinder. Well, we don't know. Too much of it. Too much added apparently, or too big of pieces, or we will figure it out. In the worst case scenario, we can just do it again. We can.
Yeah. So I'm going to try and get out some kind of powder sample. This vial is a bit dirty. Let me think about how I want to do this. Let's actually... Let's not bother with this. Give me a second. I'll get the... Actually, I've got the NMR rotor. One second.
Yep. All the questions will have to be answered in a second because unfortunately the name. Go. It's back.
Okay. Can I get this out? Challenge impossible. So this is the container for the NMR samples. So this is for solid state NMR. We have this small capsule. It's called a rotor. And this will spin really fast. The reason for that is it can average out a bunch of interactions in NMR. So I'm going to put the sample in here, or whatever the powdered stuff in the sample is. It doesn't look very reacted, but we can see in NMR if we've actually made any calcium fluoride.
It is imperative that the cylinder remains unharmed. Actually, funny enough, mechanochemistry is so violent that I don't even know if we could have a container. I imagine theoretical container, but yeah, containers are used up. Another thing, which will be funny to mention, is the gun.
Yeah, so this is a
Actually,
static
could
gun.
we? Oh, never mind. I wanted to see if people could guess what the gun does.
Yeah,
Because
I mean,
honestly, it
yeah.
is baffling.
So it fires electrons at stuff, and a lot of organic materials are very staticky, so they'll keep a lot of static energy, and they will jump around when we're trying to move it. So the static gun will de-static them.
It looks like a toy gun, but it's literally just a gun that fires electrons, which is incredible.
So this might take a few minutes. So I'm
No,
pushing it
scientists
down
love
into the
it.
rotor.
It's complete without a gun. A futuristic science gun.
Now my concern with this is that it doesn't spin properly because there's calcium metal,
Oh,
but
right.
we'll see. It wouldn't be an experiment if something didn't go wrong.
It wouldn't be a charity checkup either.
I suspect we've reacted some, and we're going to see some Teflon and some calcium fluoride in the fluorine NMR.
This does mean that in your history of research, by the way, you have had a device to remove electrons, and now you have a device to add electrons.
I mean, the device to remove electrons was also adding electrons in
Oh, no.
because it was making them into a plasma. So it was ionizing them before, and then it was ripping the electron off.
How harmful would the static gun be for humans asking for a friend? I'm guessing not really.
Sorry?
How harmful would the static gun be for humans?
It doesn't do anything to
Yeah.
you. Maybe it removes static from you, but it doesn't do anything else. I get a lot of static shocks all the time, I think because I've got hairy arms and legs and they rub on my clothes. And maybe the static gun would actually remove static from me when I'm about to get a shock. But I need to experiment with that one.
It's such an incredible tangent because it's such a simple thing. It's so futuristic. Flame is literally a wizard. Shooting electrons sound like magic to me. Yeah, have you seen where he works? Obviously. Call it technology.
I don't want to get any of the big chunks in. We don't have a whole lot of sample. Let's try this. Static gun. You can see it jump around.
unfortunately the angle is a bit upsetting. If I can like this.
So unfortunately, the one of the time limiting steps in NMR, in solid state NMR, is just putting stuff in the rotors and taking it out. And yeah, that's what I'm doing right now. And it's a bit slow, especially because I'm trying to avoid the big chunks, because they will mess with the spinning.
Well, the attempt is to understand it. At least the attempt. Static gun when a moving gun. Check over.
Stationary gun. Okay, this is probably enough sample. So we put some amount of sample in the
You can
in the thing.
actually hold it right where we're packing
Yeah?
sample because that's where the
Okay,
focus
it's
is
focused on.
anyway.
Okay. I don't know if you can see that there's a darker region. That's where the sample is.
Yeah, I think it's barely visible, but it is visible.
Yeah. So now I'm just gonna put the lid on. Is this okay? Let's just clear up some of the edges. Okay, I need tissues. Could you grab that green box of tissues?
Yes. We can see in the adjustment set, so yeah. That's the same.
Okay. I'm trying to put this cap on. Sometimes it's very tricky.
It is like absolutely
Yeah.
so.
So the reason we use very tiny containers for solid state NMR is because we want to spin the sample. And the reason we want to spin the sample is because there are a bunch of interactions in solid state NMR that all get averaged out when you spin the sample at a specific angle. So
It
a lot
is
of
just,
the
it is when you say spin the sample at the specific angle, because you have mentioned it last time, then do you mean the sample has to be rotating to a certain angle, or its velocity, like how it's spinning has to be?
it means if the rotor is spinning at a specific angle relative to the field, then all these interactions, like if you were to draw the interactions as vectors, they will all get essentially averaged into that same angle relative to the field.
I see.
I am sincerely struggling with this. Usually it's a lot easier.
Is the camera effect?
Yeah. It's also a new rotor and new caps. And we don't even know if these caps fit. Oh, have I got it? No. I just dropped it. Found it. This is very scuffed.
See, that's why when you stream, you need to make your own samples, because if you were actually doing some trying to
Yeah, here's one I made earlier.
no, if you're actually trying to measure samples that someone has given you, and then what they watch the stream and they feel like it's very scuffed, you don't want to recording. For legal reasons, actual non-stream chemistry is a lot more precise than this.
Let's try putting it down
This is all for comedic purposes.
and putting it on top. Finally. Okay, the cap is on. All I had to do was a completely different technique.
Then
So we have
you can
a
move it
yeah,
further
we have the
away.
cap on the thing.
slightly further, actually, so
Okay, like
small.
here?
There we go. Yeah.
So it might be hard to see, but the cap has these like fins pointing out, and the NMR probe will blow air on the fins and make this spin really, really fast. So this one can spin up to, I think, about 14,000 times a second. We usually only go up to 10,000 because otherwise there's a chance it might crash, and we don't want that. So we're going to spin this at 10,000 rotations per second. Before we do that, let's start another reaction. What do you think?
I would reckon just the backup reaction.
Yeah, I mean, hopefully it does react. But we'll see in this. We'll see what we get. I'm gonna empty this container. Yeah.
Camera then, for more desirable angle.
I'm actually just gonna pour it all out. Pour one out for my boy. Okay. Now, what I'm gonna do is I'm gonna take some smaller pieces of Teflon, and we'll just take a bit.
Region.
This should be reasonable.
And the water white is flame.
Hello. We need to cook. Okay. I'm putting Teflon in.
For everyone who newly joined in, allow me to summarize this part of the experiment, which is PTFE is Teflon.
Yep.
The Teflon you are familiar with, that's Teflon exactly. And what we are effectively doing is important part of information is least reactive plastic, and what we're doing is we're reacting it using mechanochemistry, and mechanochemistry is exactly what it sounds like. It's chemistry where the thing causing the reaction is mechanochemistry. We can use we use a staple tool from mechanochemistry. I mean, you're not wrong. If you hit, you get yourself a sample and you hit it with a hammer.
Okay, I suspect this will react a lot better. I'm just worried about there being an excess of calcium. Let me get smaller pieces of calcium. Actually, I can just pick the small pieces from this.
Maker is so desperate, he's now making React content.
Yeah, this is actual React content. Oh, it's fine. It's gonna be fine. It just needs to be black at the end, and then we're okay. So I'm gonna tape this together really quick. I'm gonna swap gloves.
Well, let's just take off gloves because I don't think. I'm not trying to touch something. We're on Earth. This whole planet is an excess of calcium. Well, that's trivializing.
So the reason I didn't use an exact ratio is because we've patented this reaction, and it would be a bad idea for me to show the ratio, the perfect ratio, on a live stream. But it is a very easy ratio to work out, and that would make it definitely react. So we're just eyeballing it for the sake of content, and we've got content now because it failed. So.
Like the positive spin. I mean, yes. What we're doing is we're trying to demonstrate science, and a big part of science experiments not going as expected. So that was just foresight on our part.
Hang on.
I know.
I just realized I started it without the ball. And the ball is very important for ball milling. So let me try this again. Okay, tape. Let's actually put the ball in now.
Keep your secrets, magic boy. Yeah. It is a. I really don't want to gloss over the fact that it's a genuine breakthrough. The techno recycling.
Yeah,
We're
so
talking about very casually, but that's mainly because Flame does it on a daily basis, and I just have spent so much time with him that I just react to casually, pun intended. You're welcome.
okay, let's take this sample and do some NMR.
Yes.
Hopefully it spins. If not, then I'll be very upset.
Hopefully it spins.
Yeah.
Well, once again, we need to move back to the NMR room with Big Magnus. Everyone, don't panic. There's no reason to panic. Just give me a second. I think it's fine. Okay, we are back. Unfortunately, other people also use the lab, so we have to be a bit more cautious and quiet and careful. So, we're back. Okay, so everything seems to be fine. Everyone is still watching. I'm glad none of you left during I'm glad none of you leave during the intermissions because, well, we do need to move often. That happens. Now,
So,
I figure we cover the under the magnets, right?
yeah, let me just point it down.
Yeah.
So I'm going to show the probe that goes inside the tube.
Yeah, so these are the gas lines. I'm going to repeat everything that Flame says because what you all have to realize is that the big magnets that we mentioned on the very beginning, if you know anything about electromagnetism, then you know having electronics around massive magnets, let's just say best case scenario, they get wiped, mid case scenario, they get broken, and worst case scenario, they get sucked up into the massive magnet, and in that scenario, I'm on the hook to pay for a couple £1,000,000 just for a magnet, so I don't fancy doing that, which is why we need to go about it this way. Right here we do have the probe. Yeah, Flame just basically dropped the probe, as you can see. It should be, we can bring it closer, I think, and examine, right? We can bring it closer and examine.
Yeah. Let's put it up.
Okay, let's put it up there. So let me just
I've got my microphone back.
switch the angle, like so. The camera's off right now, simply because I want to reposition. Okay. 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 There we go. And there we are. Right here we see the probe.
Yeah, so got the NMR probe. This is basically where the whole experiment happens. You can see actually there should be a sample in here. If I tilt it at the right angle. There we go. That was the sample from before. This whole thing will, for one, it will spin the sample, which averages out some interactions in the solid state. But also this connects to some radio frequency power lines and it will fire radio waves at the sample. And this will also measure the signal that we get back from the sample in response to the radio waves. So if I open this up, we can see a bit better. We can't see everything, but we can see some of the tuning rods that are traveling up through, and there's just a bunch of circuitry. um, yeah, there's capacitors which will change the frequency ranges of our radio frequency pulses, and in this section is where the sample is actually held. Yeah, there's not much to it.
It is comical how much time we spend on just a giant magnet and
Yeah.
this intricate piece of engineering, which is like,
Yeah.
yeah, there's not much. to
And
mention.
obviously everything in here is non-magnetic, because otherwise that would be a big problem. So
For obvious reasons.
I think stuff is made of
Right
gold
now,
and
I mean,
copper.
one thing we could mention, which wasn't really here, is at the bottom the gas inputs.
The what?
The gas inputs at the bottom.
The gas.
Yeah. Do you
Yeah.
reckon that would be?
Yeah, so there's these two lines are for the gas inputs. So one is the bearing one is basically gas blows on the bottom of the rotor and makes it levitate, and the drive blows on the ridges on the cap and makes it spin. And so both of these will increase when we're spinning the sample. And yeah, there's also a cable that goes into this spin detector, and this will read changes in the surface of the rotor. So these ones are marked very slightly so that they will reflect slightly more light on one half and slightly less light on the other half. And what that means is the detector will see the light goes down and then up and then down and then up, and it knows each cycle of that is one rotation of the rotor. So that's how we actually keep track of the rotor speed. And I'm going to put this in a container.
It does make sense that you couldn't really achieve standard motor, electric motor rotation in a giant magnet.
Yeah.
That could
yeah.
prove to be tricky. So it makes sense you have to do with gases.
Yeah.
Which, once again,
So
are a lot more tricky to
This
make.
is our sample. Let me put the lid back on.
Right.
And I'm going to just drop our sample in the top. Can the camera see?
It can. I'm just moving it because the angle
Yeah.
wasn't very flattering and I feel bad about it.
Okay.
There we go, yeah. Okay.
Yeah, so this just goes in the top like that. And I need to just get it to sit in at the right angle. And that should be good. So, should we put this in the magnet?
Yes.
Yeah. I'll take my microphone off.
Just there we go. And then we put it in the comically large magnets. I would say, I think everything can be seen. So the important bit is the reason why it was falling out so slowly is due to effect, I think it's lenses law, although I'm not certain. Flame will tell you in a second. But the whole bit is that it's basically slowing movement. So it would fall down really slowly, but also in order to push it back up, yeah. As you can see, it is falling. There is nothing stopping it. It's not friction, it's magnetism. But it does also mean that if you want to put it back in there, it is actually really, really annoying. And so then what we need to reattach is all the gases, obviously, and data lines. Because gases, as I mentioned, are necessary in order to spin the sample around, because once again, you cannot have magnetic motors in a giant magnet, and every single motor, electric motor, is magnetic. So that's why the gases go in there, and the data lines go obviously for data, because after all, we are running an NMR experiment, which means we would like to measure some spectrums. We'll make it as way closer to the machine with the camera and mic than what they allowed me. So that's why I'm guessing this is given straight was not the case. Yeah, but I am functioning under special make-it rules, which is why I get to move the camera so close to the NMR.
So, should we do some
Lenses,
experiments?
yeah, on the side, just before I forget, lenses law, right?
Lenz's law, yeah.
It is. Okay, good.
It creates an opposing field in the direction of in the
I was-
opposite direction to the movement.
Yes, I was doing some talking as you were putting it in.
Yeah.
If you don't mind, I'm going to put the camera like so. And now we can focus on the theory of NMR, right?
Yes. Well, we're going to do the experiment.
Oh, should
Um,
I put the camera onto the screen?
Yeah, on the screen. Give it a sec, actually. I'm going to find an experimental copy. This should be
Professional.
I mean, we copy the experiments because what's the date? 15th.
There we go.
Let's do 10. Or is it 8 kilohertz?
That's not quite horrendous now that I think about it. Let me see if I can make this a little better. No. No, it's not much better. I could increase the shutter speed. No, that's a problem. Good enough. Good enough.
Sorry, I'm just making some experiments.
But you're the one who's calling. I don't
And
think
let's do
anyone.
carbon as well.
I don't think anyone minds you doing experiments right now.
Yeah. Do we have carbon? We do. We don't. Okay. We can do fluorine carbon cross polarization. Maybe. This one probably won't work because it's very low signal, but we'll try it anyway. Actually, this shouldn't work. Let's just do this, yeah. Okay. We can look at the screen now if you didn't already have the camera on it. Okay, camera's on it. So, first things first, does it spin? So this is the spin menu. I'm going to set it to 2000 first and see what happens. It can take a sec. When this drive pressure goes up, hopefully it will be spinning. Okay, this looks like it's not properly in the probe. So I'm going to take the probe out and shake it a bit, and then it should be fine.
Okay.
You can watch me if you want. I'm not going to take it all the way out. I'm just going to unplug a couple things. I need to take my microphone off.
Yep. I was about to say. Just. Once again, the lens is low in motion, or rather lack thereof. 30 spins per second, right? Yes. hertz is a measure of how many times something is happening per second. And so, right there. I'm just gonna click this button. I'm just putting it in again.
I can see it's in because the number just went to 1 hertz, which means it's detected something.
Oh, that makes sense. You couldn't see it on the screen that we were just seeing a second ago. We're just going to be reattaching all the cables, all the pipes, everything that is needed. So in the meantime, I'm going to reposition the camera. We will look at the screen.
Okay. Let's try this again. Everything is going wrong.
Well,
Let's see, does it spin?
All we care for is this. All we care about is the spinning.
Well, it needs to spin to do the NMR.
Awesome. I mean, yeah, not that kind of spin.
There we
Yes. Beautiful.
go. It should start going up. It's going a bit slowly, which is worrying. It's concerning me that it's going up so slowly.
Could it be because of
It
the calcium?
suggests, yeah, that so calcium metal is conductive, and that means that it will cause magnetic braking. In the sense that if you try and spin a metal in a magnetic field, it will try and not spin. Yeah, this doesn't look good. I'm gonna stop this.
Should we then just wait for take it out, wait for the other one to finish?
Yeah, what we can do, we can measure a different sample. We can measure a reference sample and have a look at that and see
That's a good
see what
idea.
happens. So this is stopped. Just give it a sec. Okay.
Mr. A just asked why is the rate inconsistent, but I'm not certain if they meant the hertz or the other one they meant. Why is the rate inconsistent?
The spin rate.
I'm guessing they meant yes.
Usually it will go up quite linearly with the drive pressure.
Yeah.
It wasn't doing that.
So in this scenario, if you recall in the mechanochemistry lab, Flame mentioned that calcium is magnetic after all. And this
Calcium's
is
not magnetic,
not magnetic?
but it's conductive.
Conductive.
So it will,
Sorry about that.
yeah. So it will produce a magnetic field if it's moving in a magnetic field.
There we go. That makes a lot more sense. Conductive, removes the magnetic field. There we go. And considering how beginning of the stream, we have a giant magnetic field. This can screw the movement. There we go. Beautiful. Once again, lens is low, always satisfying. Does anyone have any questions so far? That would be the perfect time to ask them. The answer about mechanochemistry, why the big magnets needed, what we're about to do, what's happening, anything. I mean, hey, you're smart. I understand why no questions. This scene always
Okay.
feels like movies where they reveal the destruction.
Huh?
No, this Mr. said this scene feels like the movies where they reveal the weapon of mass destruction. No question. I just wanted to open the well, that's good. That's good. No questions then. And cheers to that, Adrian. I will be checking them later. So, I imagine I should point the screen back again.
Yep. So I'm just gonna do a different experiment. Firstly, let's see if this one spins, which I know it will. I know this one will go up to 8,000 times a second. So let's do that. Hit go.
Yep.
And you can hear it.
Oh yeah. I don't think microphones will pick it up.
No,
but
the
it's
microphone
just-
won't pick it up, but
It's like a vacuum in another room, basically.
you hear it around 3 or 4 hertz, kilohertz. In theory, you can hear it up to 20 kilohertz because that's the human hearing range, but you can only, it tends to just get quieter. And so if you put your head right, like against the probe, you can hear it very high pitched.
I don't want to discover that I have a pacemaker by putting my head right next to the cinema magnet.
So one of the ways we actually like troubleshoot experiments is how it sounds, because we get really used to how it sounds when it's spinning. And if it's like
That's fascinating.
spinning the wrong way, you hear that it's not spinning right. And so for example, like
That-
last week,
I do have to say that does feel like the world's leading expert in NMR just putting a sample in based on sound. No.
well, like last week, we had a sample that it wasn't spinning properly. And what I realized is that as it's going up, when it gets to like 6 kilohertz, it sounded like it was at 3 kilohertz just from knowing what 3 kilohertz sounds like. And so I realized it was reading the probe wrong, and the probe had some stains on it that the sensor was reading
That's
incorrectly.
really impressive.
So it's spinning. I'm going to just copy this experiment, and let's call it. Let's do this as well. So this should work. First, we need to tune to our nucleus. This one should already be tuned because it was this experiment was done like before the stream. And so the tuning is this weird curve thing. And if I go to the magnet, I'm just going to twist a couple knobs. You can. It's a bit because I'm going to twist something on the magnet and it's going to change the screen. So I don't know what
just
you want to show.
quickly move.
You
I
get-
suppose.
yeah, I'm going to put my microphone on the side.
All right. So
So you can see when I twist this,
yep,
it's going sideways.
it is. Yep, it is moving.
And this is basically adjusting the frequency that we're using for this nucleus. So this is for hydrogen. And let me just get it out.
So the frequency you're using for the signal.
Yeah, it's the frequency for the pulse. For the pulse and the receiver, I think. I think it sends out the pulse and it detects how much comes back, and it tries to.
Frequency for
It's
the
showing
pulse.
you where you get the minimum amount of reflectance of your signal. Because what happens if you're sending signal and it's all getting reflected back, it will basically just fry the probe. So you need it to be absorbing signal. And we do carbon as well, the carbon signal. So we have an experiment, and this experiment is an echo. we're not going to worry what echo means. I think it's a bit too ahead.
Topic for a video.
Yeah.
Topic for a video.
But all we care about is that we're sending a signal and we're getting a signal back. And right now we're sending it to the protons. So I keep saying proton. I say proton because it means hydrogen one. That's just a chemist thing. Yeah, hydrogen one isotope. So if I start this, actually let's change this to 10,000. And that's the D1. Okay, so this number is telling us how long to wait between each scan. And the other number was the number of scans that I just did. So if I start this, it's going to do one scan every 5 seconds. And the experiment is set for 10,000 scans, but I can stop it whenever I want. So I start this. And what we see is this FID. So this is the raw signal that we're getting back. And so you can see it's like a wave, and it decays. And when we Fourier transform this, it gives us a spectrum. So it gives us a single peak here. These side peaks come from the spinning. So what you'll actually see is the distance between these two peaks is 8 kilohertz, which is our spin rate.
Whoa.
And there's a lot of complicated maths into how that works. But basically, we care about this middle signal, and these other peaks are just from this, but they're from the spinning. So if we weren't spinning, this whole thing would be a broad blob. But what the spinning does is it gives us like windows into the blob that are separated by 8 kilohertz, because that's our spin rate. So yeah, right now it's still doing one scan every 5 seconds, so the signal keeps going up and up. But this is already quite good signal because it's protons and there's a lot of protons. This sample is like a reference material where it's kind of an organic material and it's got some molecules in it that will rotate around really fast in the solid state. And so that means it acts kind of like a liquid in NMR, so we get really sharp peaks, and we don't really need to worry about most of the solid state interactions. When we do our like calcium fluoride, it will be broader peaks. But yeah, this is sharp because it's a special solid material. And yeah, this is probably good, so I'm going to make it stop after the next couple scans. It's done. And now we have our spectrum. And you can see it's a bit wonky on the side. That's because of a thing called phasing, which, do I explain phase of waves? I mean, the phase is how far into a wave you are, and
Observer waves, yeah.
yeah, so it's hard to explain this without the arrows. Do you remember that?
Yes.
I think we'll leave phasing for now. But basically it can adjust this, and yeah, if it's 180 out of phase, it will be upside down, and if it's 90 out of phase, it will look kind of half and half. But this is in phase, so this is good. And yeah, so we've got our proton spectrum, and we can also do a carbon spectrum. So this experiment will tune to carbon, which we already tuned it on the other channel, but let's have a look. So yeah, this window comes up with the proton and the carbon. But yeah, you can see that the carbon's pretty well tuned, so this is fine. And let's set D1, it's fine. Number of scans, let's do 10,000 scans for fun. So this is now sending radio waves in the carbon-13 range. Now, carbon-13, usually carbon is carbon-12, but carbon-12 has a spin of 0, so we can't do NMR on it. But we can do NMR on carbon-13. The only problem is only 1% of carbons found naturally are carbon-13. And so here you can see we've got quite a noisy background relative to our signal. Whereas on the proton one, it was immediately loads of signal and the line looked really flat. On here, it's basically just the signal's way less. So when we zoom in on it, we see all the noise. And so in order to get the same amount of signal to noise ratio, we would need more scans. And yeah,
Right here we get 2 peaks. Before we got 1.
this is just because of the structure of this molecule. This molecule has, can I draw it? I'm really bad at drawing this one. Maybe I can just get the image up. It's called adamantane. Yeah, it looks like this. So you can see,
one in front, one behind.
yeah. Yeah, so this has symmetry around this central point, and this molecule will rotate really fast in its site. But yeah, there's 2 carbon sites here, and I think there are 2 proton sites as well. But I think we only get 1 proton peak because they're merged together. But yeah. So we'll just wait for this one to stop.
Ah. That's a lot of waves on top of each other.
Yeah. I mean, it's always some combination of waves, right? So
Makes sense, yeah.
yeah.
Oh, it's 2 ice per section.
So we've got our 2 peaks here. And so this material is a reference material. So what we'll use is, we know that this number is meant to be 38.48. And so one thing with the magnet is that the field will change over time very slightly. And so it means that you need to keep re-referencing. Because maybe if we did this a week from now, it might be 38.53 or something. And the accuracy of the frequency is really important for doing the NMR. So we use this reference material so that we can set this peak to the correct frequency and then do a bunch of experiments. Yeah. Should we go back to the lab, do you think?
We can, yes.
Yeah.
Do you want to show? Oh yeah, I suppose we do want to show anything in labs, no? Yep. I reckon we can go back into the lab. Before we do, let me see if anyone has anything. So right now the experiment is being done with hydrogen. No, would anything change if the nucleus also had the neutron? I suppose not, since the neutron doesn't interact with charge phenomena.
But anything change if the nucleus also had a neutron? It does change because neutrons have spin. And so when you have a different isotope of the same element, so the same number of protons with a different number of neutrons, then it will change the spin of the nucleus. And so this is why carbon-13 has a spin of half, but carbon-12 has a spin of 0, because they've got the same number of protons, but they've got different number of neutrons.
Mm-hmm.
It's the same as well. If you had a neutron on the proton, then it would be deuterium, hydrogen 2, and that has a spin of 1. So the spin changes.
Yeah, and that appears to be it. In way of questions, my brain has. Thank you. Well, you were thinking of charge. You were thinking of charge. Neutron has neutral charge, hence where its name comes from, but charge is not spin.
Yeah, so
and
most
right
particles have spin.
Yeah, right here we're concerned with spin.
Yeah.
And I suppose that is it. In that scenario, we will move back to the mechano lab, I reckon. Where we will...
I am aware it's getting quite late. So maybe we try it, we see if it's reacted. If it hasn't reacted, then we probably just talk a bit about some NMR theory and then we're done. if it has reacted, then we do the NMR and we see what we get.
I would say that's fair.
Yeah. Okay.
We'll be back. Wait, why did... Oh, hold on. Why the two peaks first before
Two
Jasmine?
peaks because there's two different carbon chemical environments. So what NMR is looking at is essentially, can I explain this verbally without drawing it? Do I just draw it?
Jasmine knows chemistry, so I imagine
Okay,
they could...
yeah.
visualize.
So any nucleus will be affected by the magnetic field some amount, and that will give us our frequency in NMR. But if you have more electrons or less electrons around that nucleus, it will change how the magnetic field interacts with it. Because for the same reason that our calcium will slow down when we try to spin it, a cloud of electrons will produce an opposing magnetic field when it's in a field. And so, because the electrons are moving around.
Could you then show the particle, actually the molecule,
Yeah,
on
yeah.
the screen again? Because I feel like that would be for visual aid. So
I don't know why it's disappeared.
the answer might be no.
Wi-Fi has just died.
It is comical
new
that you
tab.
say Wi-Fi, you know, from Wi-Fi, we are actively streaming in this room.
Interesting.
Worst case scenario, I can, I suppose, show it on the stream.
Yeah, it's just not showing. That's not it. This is a different molecule. Now it works. Okay.
That one tab which has been like...
Yeah. Yeah. So it's this molecule.
And so basically it's two different environments. So is it like corner carbons and
Yeah.
inner
So
carbons?
it's these CH2s and these CHs. So the
Oh, right. So
this carbon has 2 protons and is bonded to 2 carbons, and this one is bonded to 3 carbons and has 1 proton. So they're different chemical environments because they have different electron densities around the atom.
That does make sense. You basically have two different kinds of carbons here because it's symmetric,
Yeah.
in a way. And so, well, it's literally symmetric and also symmetric in a way. And so that means that there are only two kinds of readings you can get. One for the carbon bonded to 3 of the carbons, one for the carbon bonded to 2 of the carbons. Jasmine. Yep, they said, okay, got it. That was a good question, I like that question.
I think the follow-up question on that is why they're not 2 proton peaks. And I think the reasoning is because when you have protons, the general chemical shift range is like 0 to 10 ppm, which is just our unit for the frequency. And I think both the environments in adamantane are very close to each other, and so they just kind of form one blob here. So that's why we see 2 in carbon but not in proton, just because it's a very small range. And you can see this in liquid NMR, but you can't see this in solid state. So yeah.
That makes sense. So in that scenario, we are going to temporarily go for now again to pick up the sample.
Yep.
And we will be back in 5-10 minutes, something longer.
Well, we have to unpack we have to take
That
the
will be
sample
longer.
out the rotor and
Yes,
then
fair.
put the new sample back in the rotor. So are you trying to decide if you should bring the camera all the way into the lab?
20 minutes, I reckon. Because I'll be honest, you all have seen it again and again. Give us 20 minutes. Or you know what? Actually, change your...
I'll be back in a bit. Hopefully,
Yeah.
5-10 minutes.
All right.
See.
Yeah. Actually, change your plans because there is no point in me going with flame. No, you can go. Don't worry. There's no point in me going with flame, so I just figured that I might as well stay here. Chat to you all about. So, is there anything that I can explain? They really are having Teflon for dinner. Don't worry, Grandpa. Still, when I get home, I read. Don't worry. Oh, the pictures are going well. So, Since we have a fair bit of time, we can also go back to some of the theory. I imagine moving charge in the field can make a field that is in the same direction as the surrounding fields and would accelerate it, and thus creating energy from nowhere. I am not certain on that on its own. I would guess so. I could, if you want, I could derive it from my goodness, I've got the name. The four equations: two with cross del and two with displacement del. My lord, I forgot the name of the scientist. I'm sorry, it's been a long day. So, what are we doing? Chemistry student. Wait then, Rodrigo. We are doing a little bit. Let me just move the camera, I suppose. That will show you a bit better. We're doing a bit of mechanochemistry. I don't know if you're familiar with the field. Mechanochemistry that breaks apart Teflon, actually. Basically, you have your Teflon, you use calcium with the Teflon, you perform mechanochemistry, fluorine bonds with calcium, and what you get out is just some wacky carbon chain. The carbon chain isn't important. What is important is that you have managed to break down Teflon, which is, least reactive plastic. And then what we are doing afterwards is we are running it into this machine right here, this really comically large magnet. This entire thing is a magnet with some equipment on the inside in order to do NMR. There we go. I feel like this could be a nice screensaver us waiting. There we are, why not? You can look at the bottom of the machine. Hey, make it what you want for dinner. I mean, pizza's idea sounds great. New sample time. Well, it's the same sample, it's just... I mean, okay, it is a different sample, but the same sample. You get what I mean. Unless you don't. In which case... Why do I feel more sleepy after coffee? Do I need more? Not certain. Consult the doctor. Don't ask random people online. 90 pence pizza. If you can find 90 pence, my goodness, I would. Sense. It would be over €1. That's ridiculous, actually. When you put it that way. How are you all enjoying the stream, by the way, so far? Because we could do this more often. However, you have to realize that more often still means your microphone's a bit cracky. Why is my microphone a bit cracky? Hold on. What about this one? Is this one better? There we go. I don't know if this one is any better. It's just, I just picked up the other mic. They should be the same exact microphone, but I placed it a bit higher up. Okay. The reason my microphone might be a bit cracky is because there is a lot of sounds in the background. I can actually unfilter for a second the audio, and then you can see, or hear rather. The stream is great. The stream is great, you say. Well, I'm glad. As I mentioned, we could do these kinds of live streams more often. However, you do have to realize that it is quite a great expense for me to travel to different places, do these streams, so unfortunately that is the restriction. But I will try to do them as often as I'm able to. The stream is great. I'm really glad with the part of flamers on camera. I know, right? I can be. I see the background noise. Can you? I haven't even unfiltered yet. If you want, I can. Let me just... Because of the lab. I mean, it is because of the lab. Now I disabled the noise suppression, and you can hear the lab in its entirety. Yeah, we're still live, Lycan. We're doing science. Flame just went to extract the sample from the mechanochemistry lab, and then once he's back, we're going to use the machine you are looking at right now, and just zoom in, or zoom out rather, a bit, this machine in order to perform NMR on it, which runs again. Scientists doing science, exactly. Putting in all night in the lab. I wish one day. I would very much enjoy being in labs. It's such a shame that I don't get to do it quite often. Normally I need to break in, which is such a hassle. That's where the cracking comes from. Yes, there's a lot of machine noises all around me. What happened to the charity organization? Did they get approved and stuff? It has not been declined, just that, how should I put this? Well, it's not complicated. It's just that there are very specific bureaucratic procedures that have to be followed, and they are extremely convoluted and complicated. And I first applied in December, and then I got a response back that I applied incorrectly. So we applied in December again, and once again, a response that applied incorrectly. So then we applied in January, and then they had a month to reply, which they took, in order to, in February, tell us that we applied correctly, but there was a mistake. There wasn't a mistake in the founding document, only there was ambiguity in the founding document. So they tell us to apply again. So we did apply again in February, and in March they told us that there are a couple of documents missing. So hopefully in April it should already exist. Although that is what I said every single month before, because I don't know what they're going to throw at me. They could just accept it right now and the charity will exist, or they could reject it, in which case, well, I'll figure it out. I'll figure it out, don't worry. Can you make the filter less aggressive? Maybe that will reduce the cracking. Unfortunately, filter is a binary. It's either on or off. There is no spectrum to work on. I'm worried now. Don't worry, I'll figure it out. I hope you do make it. I will. Hey, I have so far. I faced greater challenges and managed to pull through. My job is to pull through, so I do pull through. Don't worry. There's too much riding on this for it to not work out. Failure is not an option. But yeah, that's the experiment NMR. I will be making videos about it. Don't you worry. If you don't understand everything this stream perfectly, don't worry. I'll be making videos about this. At the same time, there are a lot, and I mean a lot of topics we are not covering today because that would require us to go too much in depth. Flame has a brilliant, and I mean brilliant, visualization and explanation of this entire process. I could feel myself with the cracking noise. Yep. What are we doing? I just joined. Well, you seem to type to push through. I appreciate that. I take it as a compliment. I appreciate that. Call me renegade. Basically, first we did mechanochemistry, which is a kind of chemistry that's guided by the mechanical forces. The reason why I just got shocked by static electricity. I could really use that gun. It's Ren. Oh, hi there, Ren. Then hi. First we did mechanochemistry with Teflon. Teflon being the least reactive plastic, but mechanochemistry with calcium can react it because mechanochemistry breaks apart the Teflon chain, and then fluorine reacts with calcium, binds together. What you get is that plus carbon chain, and that means that we are reacting the least reactive plastic. Afterwards, what we do is we can put it into this machine right here, which is a giant magnet. It's not only giant magnet, but it's an NMR machine, which obviously requires the giant magnet in order to work. And once you place it into this can cause the spins to separate into two separate energy levels. And once they do separate into two separate energy levels, then camera's a little unstable and like that. Once it separates off into two separate energy levels, it means that you can give it energy and, thanks to quantum mechanics, figure out onto which level it hops, which gives you the distance between separation. I know I'm not explaining it really well. Sorry about that. Message me when I still have dinner ready. All right, you can start without me, by the way, Remco, because I do understand it's been a long day and I don't know if you have eaten. So you can start without me. That'll be absolutely fine. I don't think that there's understanding. That's good. Once again, videos on the topic will cover it much better. My ears just got blasted with an ad. Sorry about that. I know the live stream is a bit quiet. It was a good explanation. It was a quick one. You have no idea just how good the visualization of this experiment can be. You will need to unfortunately wait a while because I have a lot of things to go through, but don't worry, I will wait. I do mean it, Remco. It has been a long day, like genuinely. It's not meant to be. I don't want to bait you into politeness. I do mean it. Like it's absolutely fine. It has been a really long day. Okay. What happens if Britain? What happens in Britain stays in Birmingham? That is true. Yeah. What happens in Britain stays in Britain, what happens in the Netherlands stays in the Netherlands, and what happens in Germany stays in Germany. Those are the rules, we all know this. Well, in the meantime, as we're waiting for Flame, I reckon there is no better thing to do than to. There is so much static electricity in this room. I imagine it could have something to do with all the magnets. I imagine we could go over. Where is it? There we go. So special relativity, right? I think the place where we can. No. Ah, the Quaternions I see. My goodness, you have a sharp eye. Golden star goes to Ren. Golden star goes to Ren for actually noticing. I keep getting shocked from my camera. This is horrifying. I don't like this. I don't enjoy it at all. My camera keeps shocking me. That's like I don't mind whatever. I don't mind it. What I'm worried is that my camera is actively frying. Well, happens. But yeah, once again, I want to say, Bren, really good eye for noticing the Quaternions. Wait, when were you in Germany? Briefly. Well, I mean, 2 months ago. 3 months ago. Is old Remco with you in the lab right now, or is he not making it possible? I like Astrid as you are respecting the rules of the Tenet. I charged some gravitons and really lost now. Yeah, we separated. I just decided to break into a random lab. I don't know where Remco is. Remco is on a whole other side quest looking through gravitons. I'm not teaching GR to make it, yeah. Exactly. That's shocking. Oh, please. The camera glitched a little. Don't mind that. That's fine. I'm saying that's fine. Worst case scenario, I die in this lab. Oh, Remco, we should have taken life insurance. That would have been good. Wait, okay. The man, the myth, the legend is back. My camera keeps shocking me.
Shocking you?
Yeah.
Like static?
Yes, a lot of it.
Interesting. So,
Worrying. Is this fine? Yes,
yeah.
yes. Good.
So we did do our reaction. It came out as a black powder,
Which is good.
which is good.
Which is good.
And that means
Would you
that
like to
there's
show
carbon,
right here, roughly.
and it should also mean that there's calcium fluoride.
Can I?
So
Just this, I imagine, just to show. Right here. The sample is absolutely tiny, so I imagine it won't be really visible, but it exists.
yep.
So you're gonna put it in
I'll
now?
just put this in the ground.
All right, that's fine.
Okay. Let me just check. Oh, okay, it's still spinning.
Oh well, that explains a lot. Could that be the reason for the static, actually?
You mean your camera?
Yeah, it was a lot of static and it was building up
It
constantly.
could be the power socket might be like a high power.
It would have to go through my laptop to the camera though.
I have no idea.
Well, yeah, whatever, it's
Maybe
fine.
there's just static in this room.
Yeah. I mean, you have been standing still a lot.
Yeah.
My goodness, I blame Ash for me making these kinds of jokes now.
So we obviously have to wait for it to stop spinning. Otherwise, it crashes.
That makes sense. I like how Figure summarized it. Teflon plus calcium and a lot of shaking.
Yeah.
Basically nailing it. Glad you've paid attention.
Stopped now, so I'm going to take it out.
Does Flame have any particle? particle accelerator in this lab?
In this lab,
It depends how broadly you define a particle accelerator as well.
electron compound.
Yeah, like it always depends how broadly you define the particle accelerator, because most of the time when people say particle accelerator, they mean the kind that theoretical physicists use. But particle accelerators that chemists use are a lot more common. Once again, depends how broadly you define it. Static flavor for the weapons. Do you have a ray gun in the lab? Oh, there's an electron gun. Is that enough? Or do you want a photon gun? that's just a torch. I'd argue that a magnet is a particle accelerator. I mean, not wrong, not incorrect. Reaction. I was so fascinated by that, I showed it to my father. Well, figure, do you fancy getting yourself into physical chemistry?
Sorry?
No, I'm talking to figure right now. Because hey, if you're fascinated by it, I would suggest you pursue it. Why not? Right.
Let's try and spin this.
So, camera on the screen, I imagine.
Are you ready?
Yup. Well, I dropped the camera.
I think it's not in.
It's not in. It's not spinning.
Yeah.
That makes
So
sense.
I'll just give it a shake. I thought it was in because it went up when I dropped it in. That's a static thing.
That's not what has, yes. Uh-huh. I'm trying to call I mean, a friendly science group. I would say that it would be nice to see a lot more cross-collaboration between different fields of science, which I suppose would be the theme of this checkpoint. Yeah, definitely went up this time.
Yeah, but I think it's just going up because I'm shaking it.
Oh, like that makes sense.
I think it's.
I haven't eaten since 9 a.m. Well, I haven't eaten since yesterday. It's not a competition, people. It's not a competition. Just eat when you're hungry. That's it. I used to think you're really tall that Nancy Miles would repose, but now you still have no confidence because you're short king. Yeah, I know.
Okay, let's try again.
Promising, I think. Or, well, I spoke too soon.
No, just give it a sec. The drive pressure hasn't gone up yet. Okay, now it's going up and nothing's happening. I am gonna try something. I'm gonna try marking the rotor with a pen, because it could be that it's not detecting it properly.
That makes sense.
So, let's try again.
Okay, take care of yourself, please. I appreciate all of your sentiment, I really do, and concern. I really do appreciate it, but don't worry. Once I'm done with my work, I will. There's a lot of work to be done first, though. It's fine. First, let's focus on the experiment, because the experiment is exciting. I'm still impressed. I'm still impressed with how you've managed, by the way, to notice that it was spinning at half the speed based on the sound. Like, that's such a... I mean, I know, but still, that's such an incredible feat, in my opinion. Just genuinely expert in spectroscopy based on sounds. Yeah, I find it hilarious and incredible. But yeah. In the meantime, as the sample is going back in, as Flame is marking the sample, we can go for a brief bit of a recap because what once again we're trying to do is we have our big NMR machine, we have the big magnet in order to align the spins, make the difference in the spins. Once we have the difference in the spins, we have a lower energy level, that's the more important part. So we apply a massive magnetic field. So you have two different possible spins you can have, which is always just up and down. And then if it's aligned with the magnet, it's going to be lower energy because it's more convenient. If it's fighting against the magnet, then it's going to be higher energy, which means, tada, from your two states of equal energy, all of a sudden you have different energies. Then what we're trying to measure is the difference in these energies. What is the distance of energies between them? And in order that, we need to fire a very specific photon at them, a photon with just the right frequency, because remember, for photons, frequency is energy. And so if we fire that photon, if it gets absorbed, then we will know precisely what that distance is. However, firing a specific frequency is really difficult. So what we do instead is we send out the really short pulse, which thanks to the Fourier transform, means that we're basically kind of tricking quantum mechanics into thinking that it's a whole bunch of different frequencies or a range of frequencies, which is a really clever trick, I would say. What's the most surprising thing you found out about Flame's lab after visiting it? That's a good question because when you say surprising, well, okay. There are two ways to take that question. Either something that I just didn't think of, or something that I was expecting to be contrary. And I haven't really found anything that I wouldn't expect. As in, I've never really been in a proper lab before, but I knew what to expect, and so far all the expectations have been delivered. But what was so... I would say the sheer... No, everything is expected. I feel like a more interesting question would be what I find interesting, which I would say is the whole sheer amount of machinery.
Okay.
And sheer delicacy of it.
Third time's
I mean,
the charm.
no wonder you're fit, by the way, if you did that on a
I'm
daily
not
basis.
fit. What do you mean? I'm very unfit, actually. Let's see.
Unfit to do physics. Come on.
What is going
Could
on?
it be...
It might just not be going in properly.
Huh.
It's not even spinning badly, it's just not detecting anything. Let me check the detector cable.
Can you explain a bit of the Fourier transform a bit more, like how it tricks quantum mechanics by being transverse? Honestly, Ren, I have no clue. I understand why. It's just as unintuitive to me as well. Like the explanation of the Fourier transform makes perfect sense, but I don't understand how. I imagine it would be something to do with. Let me think. I'll be honest, I don't know. I am stumped. I am stumped. Unfortunately, that would require us to go pretty in-depth on quantum mechanics. I mean, the maths would work too, I'm not gonna lie. No, the maths is really simple, because the maths is just... I will show it in a second, though, because
Yeah,
first...
I'm just going to take the whole probe out if this doesn't work. And give it a proper shape. Yeah. I think it's just not in.
So, Ren, the issue is that I can give you the mathematical intuition. What I can't give you is the physical one, which I imagine you're seeking after, which is something that screws with me too. I will need to do research on that because I imagine it has something to do with. Well, it would be something of. It would need to be some kind of eigenvalues of energy. Wackiness, I just don't understand. So, basically, Ren, the mathematical intuition is trivially simple because it is basically you have a Fourier transform, which means that when you have a wave or a composite wave or anything, it has a certain frequency, wavelength determined by wave number. It doesn't matter which way you go. The point is you have that. Then the Fourier transform, as you are probably yourself aware, basically takes in this function, and what it gives you back is it gives you another function that's a distribution of these frequencies. So right here you would have your k. Now for a perfect wave, obviously this would just mean a spike. For an imperfect wave, it would mean like this. And basically, since there is only one allowed value for us to jump in the states, because when you have two states, there is only one jump we can make, right? Anything above that jump wouldn't go through, anything below that jump wouldn't go through. That means that effectively on this graph there's only one spike, only one point that will actually make the electron go through, which means that the shorter the burst, the wider the Fourier transform, which means the higher probability of us hitting that spike. Mathematical intuition is really simple. Physical, I have no idea. I will look into it, Ren, because I imagine it could be Heisenberg's. Oh, maybe. That might be it, actually. Oh, why didn't I? Wait, why didn't I connect it together? It could be Heisenberg's. That might actually be it. I have no idea. Uncertainty in position versus momentum, momentum to energy. Well, yeah, but well, okay, no, it's a good guess, but unless like we're certain, we shouldn't say that it is, right? I would say it's a good guess, and it probably is the case, but I will need to look into it. I know you're guessing, Ren. I know, and guessing is absolutely fine. You just need to make sure that you understand how to talk about the guess, so that you don't, accidentally cause misinformation. I feel like the biggest fear you or Flame did for this stream is convincing his PI to flash into the lab for the pre-recorded video with all the camera and lighting equipment. Actually, I mean, not really, kind of. No, as for the story for another time, I suppose, but yeah. I still have to say it was a really good guess, Ren. I'll probably start looking into it. I don't know why I didn't connect the two together. Obviously, uncertainty principle and Fourier transform. That, my goodness, I made a video on it. For goodness sake, I made a video on the connection between the uncertainty principle and the Fourier transform. So I really should have remembered that. But yeah, that would make sense. That would make a lot of sense.
Okay. Let's see. If this doesn't work, then I think we give up for today.
That is fair. I feel like the scene in Oppenheimer where they are watching the bomb go off. I'm just wishing it works.
Why is it not working? Yeah, I don't know what's going wrong. It must be something with this rotor, because it's a new rotor.
We can call it that because I do also understand that figuring it out with time pressure will just take more time.
Usually when something goes wrong, it takes a few hours to solve.
Yep.
So I think we have to call it here. Very unfortunate. Well, what we could do is we can do a static NMR spectrum, as in without spinning, but it's not gonna show much
because it's solid state chemistry.
Yeah.
Solid state NMR.
Let's look at the tuning. So this is fluorine, so it's gonna be way off. I can zoom out. Wob.
We're starting the warp.
So there's our fluorine dip. If we go to proton, it's a bit off. I'm trying to determine if the sample's actually in the holder. Because sometimes the tuning will be different if the sample's not in. What I could do is take the sample out and see if this tuning changes. And if it doesn't, then it means the sample was never in the first place. Even if it does, I don't know how I'd solve it because I gave it a proper good shake and it didn't go in. So I think we just call it here.
Unfortunately, what happens.
Yeah.
And well, such is the nature. Once again, I should mention the fact that I cannot stress enough how real of an experiment it is. It is the first, I think, I've ever covered it. Well, in person, obviously.
And
Other
both
than the-
experiments went wrong, which is awesome.
Which, I mean, honestly, if anything, it's kind of exciting. For
Yeah.
this sake. The theory of it will be covered more in depth. At least everyone got a good look at the big magnet and the probe shaking. So
You can pan back to the
yes,
magnet.
that is what I reckon should be done. It could be the cable, yeah.
It could be the chair.
It could also be the chair. Just to be fair, I was touching it, but all right.
I'm only calling it because I'm really hungry.
It has been a long day. I should be also mentioning that flame was just straight up working before the stream as well. So, well, I mean, excuse to do another one.
Yeah, true. Maybe next time, instead of prepping an experiment to do, you just come when I have experiments planned, and then you
Yeah.
watch me do them.
I would say that's absolutely fair. For some kind of lighter setup as well,
Yeah.
something that will be easier to move, maneuver, and generally a lighter stream. I will, once again, everyone, remember, everything will be covered in videos of many kinds with animations and etc. I suppose, should we just walk in to say, oh,
Yeah, well, the only thing is the mics.
yeah, we need to move
Yeah,
it to
we
the
can
left.
stand next to the.
Because what you have to, I'm gonna try to catch both us and the magnet in the same one, which I hope works out. Oh, don't tangle. Not now. Alright, there we go. To be fair, I don't have no way to stop the stream actually, so... You know what, I think we might just end it here. As in... Is there anything you'd like to say before we end the stream?
Not really.
Reason to do another, this is part one.
Yeah, we'll do another one where it actually works, hopefully.
Yes.
And we'll also do some videos on the theory of NMR, because I realize it is very complicated, and I can't just explain it all by drawing stuff on a book for a few minutes.
That is absolutely fair. Next
Yeah.
time it will be, next time the experiment will work out. Everyone seems to be really enjoying it, seems to have really
Okay.
enjoyed it. So thank you everyone so much for watching and have a great day.